John Bero, and today I will be talking to you about weighing massive black holes in the centers of galaxies via spectra. So first off, give a little background on what spectra actually are. So when a source like a black body emits a beam of light, that light isn't just at one frequency and wavelength. There's many different frequencies and wavelengths all rolled into the same beam. Now when that light hits a refractive surface, the different wavelengths of light are going to be deflected at different angles via Snell's law. And as the diagram over here shows, that will lead to the light being dispersed into its separate color components, or what we call a spectrum. This right here would be an example of pretty much the most basic spectrograph you can actually create, just with one little slit to make sure your beam is collimated and a basic prism to disperse your light. Now the next step after spectra is I'm going to be looking at spectral lines specifically. Now, spectral lines are the result of interactions between quantum systems, which is just a way of describing an atom or a molecule, with a single photon. If that photon has the correct amount of energy, it will be absorbed into the atom, excite one of the atom's electrons to a higher level, and then be spontaneously re-emitted again, the same wavelength at which it was absorbed, or as a cascade of photons of smaller wavelengths, all of which add up to the wavelength of the original photon. And this diagram shows the absorption versus emission lines. Obviously, this is kind of the diagram I just showed. Just light going through a prism, you get your standard continuum emission. And if you have if you have a cloud of material here of various elements, and you shine a light behind that, some of the light will get absorbed by some of the atoms in the cloud, and those wavelengths will then be missing from your what should be continuum spectrum. Now, if you look off axis to that light source, you will just see cool gas emitting in those wavelengths that are missing from the continuum spectrum from the absorption lines. And I am going to be looking at both of those in my measurements. And the last piece is the Doppler effect, which I'm sure you all know. You've probably all seen this little cartoon before. The apparent change in the wavelength of light due to the motion along the line of sight to or from the source. Motion of the source along the line of sight, yeah. And obviously if the source is moving away, the wavelengths will become stretched out and the light will look redder. And if the source is moving towards you, the wavefronts will become bunched up together and the light will be blue shifted. All right, now if we combine those two things, spectral lines and the Doppler effect, you come to what I'm going to be using mostly in my project, which is line broadening. Now there's many different types of ways that a spectral line can become broadened. There's natural broadening, which is actually due to just the Heisenberg uncertainty principle, because the time scale for the photon emission is so small, then delta E, delta T equals a constant, so small delta T equals large delta E. And that will cause your lines to expand. There's also the thermal Doppler effect, which is just the kinetic energy of heated gas causing the atoms to move around in various directions. And the ones that are moving away from you will be red shifted, and the ones moving towards you will be blue shifted. And in that case, obviously, the higher the temperature, and the more broad the spectral lines will be. There's also something called pressure broadening, which is apparently the collisions between atoms have a deleterious effect on emission mechanisms and actually affect the emission process. And there's also perturbations from electric fields, which is the Stark effect, which I'm sure you all remember from university physics. But none of those are actually what I'm going to be using in my project. What I'm going to be using is the macroscopic Doppler broadening, as it's called. And this right here is basically a short description of what macroscopic Doppler broadening is. Now basically, if different parts of your emitting body have different velocities relative to your line of sight, then as this diagram shows, as they're coming towards you, the light will appear to be blue shifted, and if you look at the side that's rotating away, the light will appear to be red shifted, and it will shift the center of your line as such. Now obviously a spectrum is a combination of all of these, not just looking at one of them. So when you see the spectrum of the star, you'll see basically all of these added together, which will give you a very broad line. And the width of that line is proportional to the velocity with which your object is rotating. And obviously, the greater the rotation, the more the line is broadened. So using this, we're now going to go a little further, actually. Yeah. So using the spectra I've graphed and gotten, we can calculate the widths of the lines and then use this handy equation here to get a line of sight velocity for them. Now that equation can be obtained just via the equations of Doppler shifts. And that is going to be one of the central equations I'll be using in my project. All right, now to my actual project. What I'm trying to do is look at spectral data, plot it, determines, first of all, where some of the more prominent spectral lines are, try and determine how broad they are, use that broadening via the velocity equation I just showed you to get a line of sight velocity, then use that coupled with some of the geometry of the system to try and estimate a mass of the central black hole. Now, the galaxies I am observing are M31 Andromeda, M32, a satellite of Andromeda, and M87, which is the brightest source of the Virgo cluster. Now, I'm sure many of you are wondering, why not use the nearest black hole? But there is startlingly little, even radio spectral data for it, and obviously no optical data due to the large amount of dust in between us and the galactic center. So unfortunately, I could not use that one. So M31, M32, and M87 are going to be the three galaxies that I am looking at in today. Now, I got my spectra off the NASA IPAC Extragalactic database, so there were a lot of different telescopes used to gather my spectra. These are just the three main ones: the 20-inch Hale telescope at the Palomar Observatory over there, the Kitt Peak North Observatory, which is one of those, and then the Telescopio Nazionale Galileo, which is an Italian telescope, I believe in Italy. All right, now we get to the actual data. As I said, I obtained the raw spectral data from the IPAC search tool and plotted it using UNIPLOT. So, as the titles say, here's the spectra of M31, M32, and M87. Now, the first step in this is to try and determine which spectral lines are which wasn't a super easy task, but I went with the most well-known and usually easiest to see lines, which are the H alpha and H beta lines. So, here I blew up what I at least believed to be the H alpha line of hydrogen. Now, you may notice in M87 over there that it's not quite where the center of the line should be, as the H alpha line is usually at 6562, 6563, something like that. But I looked up the redshift of M87. It is roughly 0.03. Yeah, 0.03 or 0.04, and if you do the calculations out to determine how much your line center will shift due to that redshift, turns out to be just about 48 angstroms, which works out pretty well for that line. Okay, yeah, so now we have what we hope to be our H alpha lines. Now we need to determine how broad they are. And easiest way I found to do that was to try and fit a Gaussian to each one, and then calculate the full width half max of that Gaussian using the normal equation for calculating the full width half max. For this parameter S is actually the standard deviation of the Gaussian, which is calculated from the fitting. So you can see there the fits I did. Some are better than others, obviously. All right, now I have numbers for those, and I'll show you later the results. And now that was just for the H alpha line now. So now I wanted to look at more than just one line to see if my results were wavelength determinant. So I decided to look at the H beta line. And since most of my spectra only went from 5,000 to 7,000-ish angstroms, I had to get a few more spectra. So these are the spectra down towards the hydrogen beta, or H beta end of the spectrum. And again, if we zoom in now, we will see what I hope to be the H beta lines. And again, the line for M87 is again shifted, but that's again just due to its large distance away from us and its redshift. And similar to the last one, I once again calculated the full width half axis by fitting Gaussians to them. And you can see there my best fits. All right, so now that we have line of sight velocities, in order to calculate the mass of the black hole, we're going to have to go back to some orbital dynamics and kinematics, and that's probably going to involve needing a radius of some sort. So just with some basic trigonometry, I came up with this nice equation for determining the radius based on the distance of the object from us and the spectral width in degrees. Yes. So using that, I got some numbers that I put here. Now, as a sanity check to make sure I'm not doing anything too crazy, I decided to also calculate the influence radius of the massive black holes in the centers of these galaxies. Because obviously the radius I'm getting should be less than that, otherwise the gassing stars I'm trying to observe wouldn't actually be being affected by the black hole. And as you can see, well actually I got this equation, first of all, just from the M sigma relation. And obviously, in order to do this, I had to look up the actual masses of the black holes first, so I cheated a little bit. But using those, I was glad to see that all of my spectral radii were far less than the influence radii. So that is at least a good check. All right. So now, at this point, we have our line of sight velocities. We have our radii at which we have those line of sight velocities. So all we really need to do now is calculate the mass of the central black holes. And using the virial theorem, you can relate the gravitational potential energy of the system to its kinetic energy, and you can come up with that handy expression there for determining the mass of your central black hole. All right. Now these are basically all of my results. This lists the object and all of their properties, including the spectral width in arc seconds, the various delta lambdas of the lines, the radii I calculated using the radius equation I showed you. Then we have here the velocities for each of the separate lines calculated with uncertainties, because the fit gives you an uncertainty for your standard deviation, so I thought it was just best to get uncertainties in this as well. And then for each line, I used them to estimate an individual mass of the supermassive black holes. And for at least two of them, I was very accurate with my results, that being M31 and M87. M32, for some reason, I could not get as accurate, but at least for my H alpha line, I was within the uncertainties. And that was pretty much what I was going for. So in the future, if I am to continue to do this again, I would like to look at a few more spectral lines instead of just the prominent H alpha and H beta ones. Perhaps actually use some of the software I found when attempting to do this myself that would be able to pick out every spectral line and then do this for me. And that would probably give me a better mass estimation than I've gotten so far. Another thing I'd like to do would be to actually get spectra at different radii, because for some strange reason, all of the spectra I found were at one constant radius, and ideally I'd like to have them at variant radii so I could create a nice velocity dispersion versus position along or radial distance graph. And of course, I only had 3 galaxies in my sample. The more the better. So if I do this in the future, I'd like to add at least double digits to my galaxies, and then try to make some sort of black hole mass versus galaxy size graph to see if, as I know it's been done before, to see if my results fit with the accepted notions on the theory. And I guess that is all I have for you.
Thank you, John. We have plenty of time for questions.
Could you go back to one of your spectral lines? So yeah, that's good. Or the next one.
This
Yeah. So is there a reason why M87 is an emission line as opposed to an absorption line?
I really tried to figure that out, and I did not come up with a reasonable answer. It wasn't just that I picked a bad spectrum. I looked at possibly 10 to 15 different spectrums, and they all had emission lines in this wavelength.
Yeah, if you actually go back earlier, like the one with on the spectrum, you see that
Yeah.
M87 have emission lines where you got it.
Yeah, the only real difference between M87 and the other 2 galaxies that I could find in the literature is that apparently M87 is a bit displaced from its galactic center by a few hundred light years. I was trying to think about how that may influence the spectrum.
You mean the black hole is?
Oh, yeah, what did I say? Sorry. Yeah, the black hole is displaced from the center of the galaxy, sorry. And I was trying to think about how that may affect the spectrum, but I couldn't come up with any reasonable answers, unfortunately.
Which one of them is AGN?
Which one of them are AGN? That would have been a really good thing to look at.
M87 is.
M87 is?
I'll give you a clue. We get through that.
Okay. Well, that would definitely explain why there are emission lines instead of absorption lines if it's an active galactic nucleus. Yeah, that would have been really good to look at.
T, did you have a question?
Yes. So were you looking at like the spectrum of like the entire galaxy and not just the star, right? Just to clear up my confusion, that's important.
It was like the nucleus, the spectra was
Okay.
focused on.
Yeah, I think at one point you was talking about star and then you talk about gas. So
Oh, yeah, I'm sorry, yeah. So basically it's just focusing on the inner 1 arc second, maybe 2 arc seconds of the nucleus.
Okay. Another question.
Yeah.
So there's like a continuum or something on the spectrum. Did you try like removing them by fit of polynomials and things to bring like your, so that it's like,
bring the
basically
noise
just like
levels
bring
down?
the like a level. I don't know how to say it, but like
No, yeah, I know what you mean.
and
though.
normalizing it.
That may be a good thing to do for future work, is try and reduce the noise levels and then see if I can, because if the noise levels were reduced, it'd also be easier to pick out other spectral lines.
Well, I mean, it's not just the noise, but you're also picking up like starlight and emission from
Oh, yeah, okay.
whatever that you really don't care. You know, like basically just bring them to like a base level.
A
and
more
make
base
your
level.
assumption light. So would that make your fit like when you fit the light?
I'm sure, because if you
Yeah.
look, most of these weren't even they didn't even start really at the same 0 point, so I really
Yeah.
had to almost pick and guess where the best one would be.
So maybe that can have fitting this. Like,
Yeah, it would probably have
light
given me a
is-
lot better results if I had zeroed everything out.
Do you know why M87 would be asymmetric there in the emission line?
Yeah, again, I looked really hard to try and find differences in the structure of M87 from the other ones, and I really couldn't find all that much different. It's a E0 type galaxy, but other than that, I really couldn't.
Can you go back to the that's a zoom in on HL.
Non-zoom in?
Yeah. Right. So the reason is that you have other lines blended with H alpha there. You've got nitrogen 2 lines either side of H alpha.
Okay, that
So
was.
if you go back to your fit, I rather I suspect that thing that you fitted there is actually nitrogen 2.
Oh.
So, which leads to my question, did you get consistent results for H alpha and H beta for the redshift of M87 and for the black hole mass you derived? Because the H beta profile, you just flash past it there to go back to the H beta profile.
Yeah.
It looks very different, right?
Right. Well, I will say those two results were the most different that I found. So yeah, the estimated mass based on the H alpha line and H beta line for M32 were the two most different ones. Were you talking about M87 or M32?
No, M87.
Oh, M87.
Yeah,
Ah,
M87.
okay.
So
Yeah, and then in that case, I suppose it was just luck that they worked out being similar.
Did
Even though
you get the same redshift? You measured the redshift from each?
I didn't actually measure the redshift specifically at any point.
I thought you said you did do that.
I used the Doppler equations to. You mean? Oh, okay, I get what you mean. I looked up the redshift of M87
Right.
because when I looked at the H alpha lines, I saw that the centers were skewed by about 40 angstroms.
Right.
And after I did, I just wanted to make sure that was the.
Right.
So I never actually measured the redshift of
Oh, I
the
see.
other one, but I
Okay.
just kind of made sure it was.
You looked it up and made sure the line was in roughly the right place.
Yeah, because that was one of my biggest problems, was really trying to determine which lines were which, and I was kind of just going by central wavelength. Probably not a good, only that estimation, but.
So knowing what you now know, how would you reanalyze M87?
Probably try and use one of these software programs I found to pick out the lines for me, and then from using what lines they tell me, try and calculate them by hand. Because obviously, I thought that was the right line, and obviously my line picking skills may not be the best.
so going along this line, I would suggest next time you just like do the same like simultaneously with multiple lines at the same time instead of just choosing one.
Oh, okay, yeah. I
So if
understand.
they are redshift, then on them will be redshift.
Right, yeah, that makes
Right.
sense.
So you can simultaneously fit the 3 lines that make up that blend around H alpha.
Individually,
Yeah.
and then, okay.
You can apply some constraints based on the physics that reduce the number of free parameters.
Okay, that may be a good thing to look at in the future.
Does anybody else have a question?
This is not a question, but I looked up really quick on M32. So it seems to be a weird galaxy, sort of. So, I mean, it's okay if you get a weird number because it's a weird galaxy.
That was the one number I was almost like trying to contest, but unfortunately one of our professors here was the author of the paper that claimed that math. So the math law. David Merritt was one of the.
Oh, okay.
Yeah, so didn't exactly want to, for risk that he might be here, say that math might be wrong.
Yeah, well, I mean, if you're finding a mass assuming that is a well-behaved galaxy, but
Right.
it seems like it's not.
There's a lot of assumptions built in here.
So name some assumptions. I was going to ask a question.
Oh, okay.
Yeah, there's a whole raft of assumptions that go into this. So it's
Well, let's see. Where's this of you? The assumptions that I made. Well, I guess in terms of, I guess we were kind of assuming that almost, I guess, all the galaxies were edge on, otherwise
well, what kinds of galaxies are they?
they vary.
So
I guess we were assuming, I know M80 or M32 is a big elliptical galaxy. Or no, M87 is a big elliptical galaxy,
M87,
sorry.
okay.
And then M32 is a small satellite galaxy, so they're at least structurally very different. So I guess part of this assumption goes into that they're all have similar properties and similar.
Well, that may not be too bad an assumption because the black hole is in the bulge. So M31 is
Right.
right? M32, I think that's isn't that the elliptical companion satellite of that?
Yeah, it's an elliptical.
Right, so that's an elliptical. M87 is an elliptical. So that may not be such a bad assumption. But the big one, right, So, is the black hole the only source of gravitational potential?
No, it's not. I guess I was hoping because all of the radii I calculated were inside the influence radii, and that's defined as the radius at which the gravitational potential dominates over the host potential. I was, I guess, hoping that was a good assumption to make.
Yeah, actually, so you calculated that. I was like surprised that given your relatively large apertures, right, arc second or 2 arc seconds, that you're within the gravitational radius. When I haven't done the calculations, I think that's right.
Assuming I did them correctly, which I hope I did, those were the numbers I got.
Yeah, so that surprised me. And also, I was impressed that your results are so consistent with the. So those actual black hole masses, do they come from? Where do they come from? Are they actual measurements, or did I understand you that you inferred them from the M-sigma relation?
No, those ones I did not infer for the M-sigma relation.
So those are measurements by the people.
Yes, those are measurements, and specifically none of those were confirmed using this, which is kind of what I wanted. I wanted measurements that weren't exactly what I did to make sure I could get close to them.
So I use the Bero theorem to calculate mass.
Yes.
Right.
A version of it.
Right. So the numerical factor there. What does that come from? That involves another assumption, I think.
Numerical factor. Well, I know in the equations the
5, 6.
Yeah.
Also, are you assuming it's like spherical symmetry or something?
I think so. Yeah, because I think when you, the derivation of that from the virial theorem definitely makes
So
it
it's
spherical.
right. So can you write the Bero theorem on the board?
God, I hope so. Let's see.
In terms of its kinetic potential energy. Yep. Okay, good. So you have to make an assumption for the gravitational potential energy, which will depend on the mass distribution.
Right. So I guess you're assuming a gravitational potential of that form.
What is your density, like this form of your?
Yeah, because I guess that would be influence. U.
So I think the assumption you've implicitly made there is that you have the thing that contains the black hole is a uniform. The gravitational potential
Is uniform.
is a uniform sphere.
Right, which is very much not always the case.
Well, actually, you're ignoring the stars, so that's actually maybe not such a bad consolation for the inner particle, like a galaxy bulge, but you're really assuming that all of the masses in the black hole, so you should be consistent. You should use the point mass potential.
The point mass potential instead of okay.
But that's only a small numerical factor, so it's not going to make that much difference.
Okay. Definitely something to consider.
So people who do research on this topic, have you read any of those papers, by the way?
Yes.
Yeah. Okay. So obviously they do a much more complex analysis, which involves trying to figure out what the mass distribution is.
Beta velocity dispersions, I think.
Exactly. So that they can decompose the contributions to the potential from the stars from the mass potential into the black hole.
In order to do that, they do need spectra increasing radii, right?
Right.
Right. Yeah, that was the problem I was kind of running into.
The light distribution. Right. And generally with much higher spatial resolution too.
Yes.
Any other questions?